So this video is going to cover chapter 9.2 section 4, which is all about Bayesian intervals. According to statistical inference by Casella and Berger, a Bayesian interval is just describing interactions between the confidence interval and the parameter. And be very careful that the interval covers the parameter and not the parameter inside of the interval. Also, it's important that all Bayesian claims of coverage are made with respect to our posterior distribution of our parameter. And for the Bayesian interval sets and stuff, we actually refer to them as credible sets rather than confidence sets. So basically, it is an interval within what is unobserved parameter falls in between with a particular probability. So that is what a Bayesian interval is.
So let's talk more about our Bayesian intervals and what it means. So to reiterate some stuff that I already said about what a Bayesian interval is, it specifically is to help us estimate and value of an unobserved random variable, such as, we'll just call it x. In this case, our x is our unobserved random variable. And some of the given information that we have is y, and y is our observed variable. Since this problem deals with a variable of x, given that y occurred and y was observed, we actually also need to calculate our posterior density. And keep in mind, this is for x given our y. We can actually find the interval given this. Using this, sorry. Given my y equals my y. And that also equals 1 minus my alpha. My interval of a to b is said to be 1 minus alpha, 100% credible for the interval for x. So basically it says if this right here is true, then we have this is true, and our interval would be a, b. And this is for a Bayesian interval.
So that was a definition of the Bayesian interval, but let's look what it actually means and how it works. So this is an example of how a Bayesian interval is actually used.
So let's look at a Bayesian interval example. So we're going to let x and y be jointly normal, and our x comes from a normal distribution from 0 to 1, and right here we have an y comes from a normal distribution from 1 to 4. So for this example, what we're going to want to do is find 95% of a credible Bayesian interval for x, given just like y equals 2 is observed. So because x and y are jointly normal random variables, we know from statistics 1 that it means it brings in some parameters, such as mu x, keep in mind that if my y is y and my x is normally distributed, that means we can actually kind of use some of the helpful things that we know from because it's jointly normal and it comes from a normal distribution. And all of these are going to be given that my y, because that's very important for this Bayesian interval. So if you look back in our statistic notes and stuff, we shall see something that should definitely look familiar and close to this. And we know that my variance of x given my y is going to be this, just because of also the normal distribution and it being jointed with the x and the y. In our specific problem, since we said that given our y equals 2 is observed, we can go ahead and plug in our y into our e and our variance. Thus, we get this. Our mu of x is 0. My plus, since my 2 is my number, because my y, then I have a 1/2. And it says y minus my mu of y, which is 1, divided right here by this, which is 2. And we can simplify this down. 0 doesn't really make a difference, adding, subtracting, since it's just 0. 2 minus 1 right here is 1. 1 divided by 2 is still 1/2. 1/2 times 1/2 is 1/4. Let's try our variance when we plug in our y of 2. Said 1 minus, because again my y is 2, I have my y of 4. Then 1 squared, which is also 1. 1 minus 1/4 is 3/4. 3/4 times 1 squared is still 3/4. Since we were talking about 95% and our 1 minus alpha is the 100%, we need to find out what our alpha is right here. Do some basic math, and we get my alpha is 0.05. Thus we get given my y equals 2, and since we're talking about that 95%, it goes right here. So since we're dealing with expected value and jointly normal distributed, we actually, since we're dealing with more of the expected value, we can find our interval from my expected value minus some number, some constant, and 1/4 plus a c. We can do this because it's symmetric because of the expected value and the type of distribution we're dealing with. Thus, then I know that kind of what my A and my B is a little bit. I know my A and B. We can kind of take it a step further and see if we can actually solve to see what C exactly is. And keep in mind, this is all given that my y equals 2. And also keep in mind that right here, this equals our 1 minus our alpha, which is also 0.95. And I have my square root right here. 1 minus 1/4 is 3/4. And I have my 3/4 here as well. And keep in mind, this still equals at 0.95. I know a negative and a negative will make a positive. I see that inside is the same exact stuff. And when I have 1 apple plus 1 apple, I get 2 apples. And it still equals our 0.95. Then at this point, all we really want to do is just solve for c and get c by itself. So I'm going to add 1. Next, I have this multiplied by 2, so to get rid of it, I divide by 2. In this case, that gets me a 0.975. I also want to divide here. So this would be to the power of -1. To get rid of the square root of 3/4, sits on a denominator, all I have to do is to multiply it by the square root of 3/4. I'm going to type it into the calculator and see if I can get like an approximation or an answer. So I get about 1.70. And this would be my c. Therefore, my interval we said was 1/4 minus my c. So 1/4 minus about 1.7 is -1.45. And my b was my 1/4 plus my 1.75, which would be about, 1.95. And this would be my Bayesian credible interval for x.